my colleagues as well. Rami, who's kindly volunteered to help with the QA, and Saurabh, who would be, covering what we do in partnership with Portkey later. So just to give you an actual introduction of what Cerebras is about, in case if you have ever not come across Cerebras before, just wanted to give you a quick speed test running Cerebras GPT OSS 120B on Cerebras, which is going to be the focus of this session, versus Fireworks, which is today the most GPU optimized solution that exists in the market with respect to GPT OSS 120B. So asking just a question on a detailed road trip plan. And you can see us on the left and we're done. So that's the value proposition, instant AI, ability to generate a response instantly to your request. And this is 10x faster than what you can get from GPU-based solution. The fundamental reason why we're able to go 10x faster is from our hardware advantage. Today, we're in our third generation. The idea is if AI's compute needs keep growing exponentially, why do we make small chips and then spend all the time to interconnect all these dice together through various complex mechanisms? What if we're able to build a giant chip that's containing enough compute and memory to power the AI workloads of the future? So when they went down this path, models were, the biggest models of those times were a few million parameters and maybe going into the 100 million parameters, as BERT did around 2018, was kind of like, an aspirational goal. And fast forward 10 years from there, we're at a stage where like models have grown, to the many trillions of parameters in terms of like, production utility, and don't even fit like one giant chip anymore. But the fundamental advantages that you get from scaling out hardware, connecting 84 dice together in a single silicon substrate, as you see here with the wafer-scale engine 3, 30 times larger than a B200 GPU, means you can pack 20 times more transistors, 350 times more on-chip memory, and almost 2,600 times more memory bandwidth. And fundamental innovations like this drive the next generation of our AI experience. And the reason why is if you have shipped, generative AI solutions or any AI-based solutions in your, work or your personal projects before, you would have typically interacted with at least a single DGX GPU server from NVIDIA. And the way the architecture works for the GPU is you have what is called the high bandwidth memory that is interfacing with each, GPU chip, which has a smaller amount of on-chip memory as well as compute that's available. So typically, if you take a B200, this memory bandwidth between the high bandwidth memory typically is, anywhere from like, 80 gigabytes to much larger. To the on-chip memory that's in the order of like few hundred megabytes at best. It's around 8 terabytes per second. So in the inference world, what you end up doing is you keep the model layers on the HBM memory, and then during inference time you stream these layers from like the HBM memory to the on-chip compute through the computations. So if you look at inference as a performance metric and time per output token, which is essentially the amount of time that you need to generate a new token in the autoregressive world, that's around 5 milliseconds for a lot of the open source models today, right? And the reason for that is you're shuttling this model layers from HBM to the compute. What happens when you could go to a chip that is 30 times larger and can deliver 2,600 times more memory bandwidth? The idea is fairly straightforward. If you have enough SRAM memory, each chip in the Cerebras LAN has 44 gigabytes of SRAM and 900,000 compute cores. So if you're able to load each layer in like, one chip or multiple chips, depending on the model size, then you have these layers really close to the compute. And what that essentially unlocks for you is an ability to like generate these tokens much faster because your forward pass in like the LLM world is essentially like a loop, right? From an autoregressive model perspective, where you generate these tokens, you feed them back to generate the next new token. And having the memory close to the compute allows you to go one level better in terms of performance optimization. And you can see the effects of this across the board. We host a public inference cloud with a lot of the open source open weight models today. The leading models like your Qwen, OpenAI, GPT-OSS. We recently launched GLM. Uh, Llama, again, from Meta is one of our popular models. But across the board, if you look at performance in terms of output speed, tokens per second, what's capable from like a GPU to what's capable on Cerebras, you would see a 10 to 20x magnitude difference in performance. Some of the leading models today, um, hitting 1,000+ tokens per second speed in terms of output speed is unimaginable on GPUs, but we routinely are able to push that to the 2,000 tokens per second performance delta. And today I wanted to spend a little bit of time to actually walk you through why that performance difference exists. Of course, it's really good to understand from the perspective of, yeah, you have a giant chip, you pack it with, a lot of memory, but what actually happens under the hood, right? To enable you to go from having a chip which has that capability to actually delivering that performance. Um, so for the simpler scenario, consider a model like, the Llama 3.1 8B, right? That's 8 billion parameters. And at the FP16 scenario, where you're considering 2 bytes per parameter to be like, the memory that you have access to, and there's going to be something extra associated with like managing KV cache. But if you just take the model alone and the memory required to fit it at FP16, that's going to be like just multiply the size of the model by 2 because it's 2 bytes per parameter. So you have 16 gigabytes of memory. A lot of people run inference on a single H100 or H200 GPU today if you're going to the cloud, and are easily able to like host this model on a single GPU. So the equivalent to that in the Cerebras world, when you have 44 gigabytes of SRAM, is a single wafer. The main difference would be you would be able to just fit the entirety of the model into the wafer because the on-chip memory allows for you to uh, host all the layers close to the compute. In practice, though, as you have seen from what I showed you in terms of performance metrics across a bunch of these models, the models have gotten so big, right? A few 100 billion parameters to even a trillion plus parameter models are common in terms of, production AI today. And that means that you need to spread this out across multiple wafers. It's not going to be the scenario that you can fit large models on a single wafer. But the value proposition in terms of being able to have the model weights close to the compute still stays the same. So you can see here, for example, GPT-OSS 120B though it has 5 billion active parameters, you do not know, depending on the type of prompt that you're sending to that model. You might need to activate a different set of, the layers. And that means you need to think about fitting this efficiently. For larger models, you tend to think about going down in terms of precision so that your trade-off is you use smaller amount of hardware to be able to scale to more users. But in the Cerebras land, the idea still remains the same. You would have chip-to-chip communication. Today, we rely on RDMA or Ethernet to do that. But a majority of the layers still fit within a single chip. And when you're doing this inference, there are certain boundary layers where you're going to split this over. And the latency in that scenario still remains much lower in comparison to running that against GPU-based solutions, as you've seen earlier as well with what you see from the performance charts. And why is that so, right? So if you look at what happens at like hardware level, from like a GPU perspective or like you know a different chip like Cerebras, you'd get much clearer answers. So today I'm going to be talking about what is known as pipeline execution, and I'll walk you through what the basics of that is and how that's applicable with the Cerebras architecture and that enables for easy scaling with a performance perspective. So if you consider a toy four-layer neural network as a representation, right? In the GPU world, as I showed a little earlier, you have this concept of HBM where you fit this model and then you stream layers to the actual chip, right? When you're running this inference compute. So depending on the model size, you may use multiple chips to run a single layer in the model. That's kind of how you split that out. In Cerebras, you go the opposite way, right? In terms of how you would accommodate the same. So you would use a fraction of the resources on a single chip dedicated to a single layer. And this is essentially the idea behind like pipeline execution generation. So you're allocating regions within the wafer where you're able to store on the on-chip memory that's available close to the compute. And depending on the number of layers that you need to fit, the KV cache that you need to manage, and the number of chips that's available to you, it then becomes an optimization problem for the compiler. The idea behind pipeline execution, though, is like fairly straightforward. Once you've mapped these model layers to the regions in the wafer, you can then get communication for free because a lot of this communication happens on chip. You don't need to shuttle that token between the compute chip to an external memory and then bring that back. You can do the computation on layer one and forward that to the other layers, which are largely going to remain adjacent to you in terms of like accessibility. If you look at a typical low latency pipeline, you know, the simplest scenario is if you consider each wafer region is processing a single token. So assume you're getting enough memory bandwidth where you're running this like local microbatch size of one, and you're using the memory to feed the compute data path at full speed. So when you think about this as a paradigm, essentially what you're doing is something akin to like a matrix vector type operation, and you're trying to maximize your memory bandwidth to make that go as fast as possible. And the reason it's able to deliver that performance is a lot of the interconnect that you see on the chip. Essentially, it's a Cartesian grid. Each compute core gets its own dedicated 48 kilobytes of SRAM, and each compute core is connected to four of its nearest neighbors in a grid. And this pattern is repeated across the entirety of the chip. This enables you to deliver a low fabric interconnect. All the communication on the chip is sent through like broadcast and receive. There is no concept of a cache hierarchy on the chip. But it's still orders of magnitude faster because a lot of this happens on silicon rather than like go between different communication protocols from an external memory to on-chip memory. And when you place layers that are neighboring to each other, as you see here, then once you're done with compute on one layer, you can very quickly and efficiently pass that over to the next layer because it's going to be adjacent. And this means that when you go between one pipeline stage to the other, virtually you don't see any latency. It's less than microseconds. For a simple autoregressive example, as you pipe through multiple layers here, right? You can see here I went from like, processing that local microbatch in layer one to layer two to layer three, layer four, and then back again to layer one to generate like the next token. And this is what enables super fast token generation in practice, the ability to very quickly, move the processed information in terms of activations to the final token all efficiently within one place. I talked a lot about doing, a small micro batch and like, life cycle of a single request. But the reality of production AI or even experimental AI today is you need to be able to accelerate a lot of concurrent requests fast. And that's the utility of like any hardware, right, in terms of trade-offs. When you think about multiple requests, how it works in a pipelined execution is subtly different from how you typically would run the same optimizations when you run them on GPUs. If you recall, I talked about mapping each of these layers to specific regions within the chip so that you're using a fraction of the memory bandwidth available, but running these resources dedicated for each layers. So since I'm just using a fraction of memory bandwidth available, I can use the extra bandwidth that's there per layer to run multiple uses. So for example, if I have, process that token from layer one and send that over to layer two, the resources for layer one are still dedicated, right? And that means I can pull in a new request to process, and that gets processed in layer one, while the previous request now gets processed in layer two. In that way, like a step function increase, I can basically increase the number of requests that are filling the pipeline till every layer in the pipeline is processing, its own particular request. And the advantage here is since it's all dedicated resources, each pipeline stage is running in parallel to each other. So this is a very simple example of how you can increase concurrency with full pipeline model parallelism just from a single chip. In practice, the optimizations that you may need to apply are more complex because, each layer may need different size of regions, like what's required for an MOE may be different from a dense layer. What's required for attention could be very different from what's required for an FFN. But the conceptually, if you take a step back and look at it, you should be able to fill up the pipeline and keep that, running with like multiple requests. And the compiler should be responsible for making all these trade-offs. So one of the optimization levers that people typically tend to utilize when it comes to running inference, especially production inference, is this concept of draft token processing. So draft models are typically models that are much smaller than the parent model that you're running inference on. For example, let's say you have like a Llama 70B model, and Llama, as you know, has like different generations of models from small to large. The smallest is a billion parameters. You could choose to, process tokens through the smaller model and get the token probabilities from that at a faster rate than going through the larger model because, there's more layers to go through. And you could then just have the larger model verifying the tokens produced by the smaller model. And if the tokens mismatch, you can then have the larger model generate the token. And this is a very common optimization strategy to increase the performance of inference. And it's multiplied, I think, anywhere from 1.5 to 2x, right, in terms of performance in the GPU world. In Cerebras, it's no different. Draft tokens do increase the performance, but you can get more gains from draft processing in Cerebras architecture. And the simple reason for that is, each layer is running its own dedicated resources. So you can have a much smaller model that's fitting just on one chip, produce tokens at a much faster rate, and you can have the larger model then fill up individually, right, on layers in the pipeline and keep verifying these tokens as they're produced. And since they get produced at a much faster rate in Cerebras in comparison to GPUs, you can run through more draft token verifications at any given point. In this example, we're showing, on a life cycle of like a couple of requests where you can interleave draft tokens from a smaller model to process, with a larger model, and in effect achieve higher user input speed using, those empty pipe stages where you can then quickly bring in and pull in a new request. So if you think about the anatomy of putting everything together, single request, multiple request, and things like, draft processing, you're enabling really high throughput as well as power efficiency because a lot of this communication is happening majorly on chip. It's a lot more efficient and you expend a lot less power per token. In practice, what this means from like an optimization perspective to serve an actual public endpoint, right, that's set by many tens of thousands of developers is a lot more complex. You need to make decisions on what type of tokens does each layer process. Are you better off with dedicating a few layers to process more input tokens and other layers to do output tokens? Or do you not care about the type of token you're processing and then uniformly consider everything across layers? As I said, like things like attention might require more compute, right? In comparison to something else. How do you then make the trade-off? Do you then end up processing, more input tokens in that scenario in comparison to generation tokens? What happens if you combine more tokens in a particular region instead of, serving a simple micro batch of one token per layer? What if I bring in more tokens? So these are all the trade-offs that performance architects deal with every day to try and improve the performance and trade that off with higher throughput to be able to process more requests at any given point of time. And in reality, it actually looks more like this, where for a particular layer, there are many tokens in that micro batch, and each token can be something of a different kind. It could be an input token, it could be a speculative draft token, it could be an output token, and you need to operate, in that microsecond latency framework to figure out what you're going to do, next. And these set of optimizations are just like, the tip of the iceberg. There are a lot more complex optimizations that you can think about from an architecture perspective to improve performance further and make these models, more scalable for production applications. And if I take even one step further and then think about what this means from an architecture perspective, right? In traditional GPU type batching, what you can do is you can increase the concurrency by sending a lot more requests because you're managing all this memory off chip and then streaming those in. And that comes at the expense of you taking a performance hit on each individual request where it can get slower. So I've just summarized this in terms of like traditional GPU batching versus like how you think about it from like a perspective of like pipeline batching that Cerebras does. So on the left, let's say you have like 8 requests and a budget of 120 seconds, typically 2 minutes, right, to serve those requests. If you're thinking about how you do that on a GPU perspective, you could either think about making them go more performant and then scheduling it in a way where like you're sending, in each minute window 4 requests. So each request could be more performant, but the sacrifice that you're then making is that you need the entire 120-second window. Or if your users can't wait, you typically then decide to send all of them in the same batch. And then you take the trade-off of certain requests being slower than usual to complete, with the worst case being that your expectation is within that time window of 120 seconds, you want all the requests to complete. If you're running the same thing in a pipeline-based architecture like Cerebras, what you typically then think about is how do I fill this pipeline so that I'm getting, each individual request to get into the wafer as fast as possible. So it's more of like designing pipeline slots and then a step function increase in number of requests that you send into the pipeline slots so that you keep the entire pipeline occupied. But the advantage then becomes that because generation can be, 10x faster once each request enters this pipeline, that means each request is going to vacate this pipeline a lot sooner than it would on like the GPU world. So you hit a saturation as you increase the number of requests that's possible. But then once you hit that saturation limit, each request is actually vacating the pipeline for a new request to come in at a much faster rate. So if you take the same 2-minute window that you had, in the worst case, you might end up with the same performance where you complete those 8 requests in that 2-minute time window. But in the best case, you fill the pipeline like 8x faster, right? So each individual request went much faster, and overall you completed this request 4x faster than you would have in GPU world in the same time frame that you were considering earlier, right? And in the average case, if you take like between the best and worst in a very simplified view and think about it, you're still going to be around 35% faster to be able to complete this task. And that's the benefit of implementing hardware level architectural changes. It lets you deliver an order of magnitude performance that software optimizations simply cannot keep up with. I wanted to take a brief breath here, and I wanted to then invite my colleague Saurabh to um, talk a little bit about what this means in practice for uh, developers, and what we're doing with the Portkey team in terms of increasing the access to this.
Sure, absolutely. And thank you, everyone, for very quick. So, very recently, we started thinking about what is the best way for us to kind of integrate with some of the best companies that kind of complement the Cerebras technology and the product portfolio that we have. And in that pursuit, we launched the API certification program. This is basically a pathway for companies to build an integration and give an opportunity for developers to use their current platform along with the fast inference that Cerebras has to provide. So I'm very proud of the partnership that we have with Portkey. Portkey was one of our first launch partners of the API certification partner program, and we have seen a tremendous success. Working with Portkey, developers love the experience of hosting their keys and managing the virtual keys on the Portkey platform while using the power of Cerebras for configuring their applications on the AI front. And at the same time, I think once you kind of bring in the service key, configure that into Portkey, you get a whole bunch of native value proposition that Portkey platform has to offer, whether it's load balancing or having, managing guardrails or enterprise grade security. Everything goes along with Portkey. And I think I always kind of think about it like a fast car moving on a fast lane. So the fast car, of course, is Cerebras here, and the fast lane is Portkey. And the end result, as I mentioned, is it enhances your developer productivity. So you are now more focused on building innovations, thinking about new optimizations to your workflow versus kind of waiting forever to get a response on your command in the keys, right? We also offer the developer API keys. So if you're interested, Karthik would definitely share more information on how you can set up your keys and start using the platform along with Portkey. And at the same time, if you have any questions on learning and understanding more about Cerebras, you can always reach out to us. We have a lot of resources and materials that we can ship over to you to kind of understand where we present, where we operate, and where we optimize the most in terms of our enterprise and startup ecosystems. And I think that's it. That's all I have from my side. Karthik,